Hello, my name is Adrian Delmeister from the University of Tennessee, and I'm going to tell you about how one can measure post-quench entanglement entropy through density correlations. This is work done with my amazing collaborator, Ben Rosenau at the University of Leipzig, and my excellent postdoc, Hatem Barghouti at the University of Tennessee. The work was funded by the NSF in the DMR program and also through DFG, and you can find it on the archive, and it was recently accepted as a letter in Physical Review Research. You can find these slides on my website, and all of the code that was used, including the data and software and scripts to generate all results in this talk, on our Delmeister Group GitHub repository. So the motivation for this work is to identify and benchmark novel entanglement measurement protocols. And the reason for that is because measuring entanglement is extremely hard, especially measuring entanglement dynamics. So entanglement is the non-classical information encoded in a quantum system. And so, for example, imagine as I have here, I have a 1D system with periodic boundary conditions, and I'm asking what is the entanglement between some spatial subregion of the system of length L with the rest, or the complement of the system. And in order to measure that in general, I would need to compute the complete density matrix, which is an exponentially difficult thing to do in general. And then I can compute the reduced density matrix by essentially tracing out only those degrees of freedom in the complement, which will give me back the entanglement as a function of the size of the spatial subregion. This is the so-called von Neumann entanglement entropy. And we might be interested in the dynamics of this quantity. How does it change as a function of time? So doing that, as I said, in an experiment is non-trivial, although there has been really amazing progress over the last number of years, surprising amount of progress. So for example, Marcus Greiner has been able to implement the so-called swap approach, which allows one to interfere two copies of the system. So I prepare two copies of the system and I interfere them together, and then I use essentially bosonic interference to identify the purity of the system, and in particular of a spatial subregion. And so he was able to do that to compute the second Rayleigh entropy, which is a slight modification of this von Neumann entropy, as a function of time for a system of rubidium atoms, bosons in a 1D optical trap, and was able to see this kind of linear growth of entanglement before saturation over here. Another approach, which is quite promising, is the use of random measurements, so-called unitaries, which allows us to understand the entanglement between sites. So here, this is a region that goes from 1 to site I. Each of these curves corresponds to a different time. This is a pretty amazing paper. I'd encourage you to look at it from a number of years ago. And finally, in cases where one doesn't have access to this density matrix directly, or these Rayleigh entropies, one can use so-called entanglement witnesses, or types of functions that might provide some information on how entangled a given system is. And my collaborator Alan Tennant recently showed that one can use, for example, the quantum Fisher information to understand entanglement in a quantum spin chain, basically purely from neutron scattering experiments, obtaining access to the static structure factor. So all of these are kind of amazing experiments, and they're all extremely difficult. So why would we want to understand entanglement dynamics? Well, it turns out that we can kind of get a picture of how statistical mechanics observes from unitary time evolution by looking at thermalization coming from entanglement accumulation. So if I imagine that I have some system, so this is the same system as we had before, but now not on a ring anymore, just stretched out, and I'm interested in this region of length L. If I make a sudden change to the system at time 0, what's going to happen is I'm going to create quasi-particles. I'm no longer in the ground state of the current Hamiltonian. Those quasi-particles will propagate with some velocity. I'll have a sort of a light cone here. And what I'll find is that the entanglement as a function of time should indeed grow linearly, just as we saw in the experiment, before saturating at a so-called volume law. And this volume law right here, the prefactor of this volume law is extremely important, this steady state prefactor, because it gives us information on the transition to this extensive entropy, which is connected to, for example, the thermodynamic entropy. So this is one way where we can think about some type of thermalization in an otherwise closed quantum system. And it turns out that actually we know a lot about thermal entropy in a particular model, the Luttinger model, which is really a universal way to describe all systems in 1D with this kind of universal linear quantum hydrodynamics. So whatever kind of high energy microscopic model I might have in 1D, I can basically map it on to this very simple Hamiltonian, where instead of keeping track of the locations of individual particles, instead I just look at deviations from a local background density. I can write things in terms of two fields, phi and theta, which correspond to sort of fluctuations in the local density and the local phase. And by doing a mode decomposition, this thing essentially allows, forgetting about some zero modes, allows me to write any 1D quantum system, either bosonic or fermionic, as a system of non-interacting harmonic oscillators that have this linear dispersion. And this velocity v here is the same velocity that we already talked about. It would be this quasi-particle velocity. So the excitations in all these 1D systems are purely bosonic density waves. And we know a lot, because of the fact that these bosonic density waves are non-interacting, we know a lot about them. In particular, we know how to compute their thermal entropy. And it turns out that the thermal entropy of the underlying one-dimensional fermions can be captured exactly by the bosonic degrees of freedom, where this NQ here is just the boson occupation, the number of density waves with particular momentum Q, and this is just the normal free boson entropy formula. And this mapping under the Luttinger model, at least at low energies and long wavelengths, essentially doesn't lose any degrees of freedom. And so there's two natural questions that we can ask. One is, does this relation hold in the non-equilibrium steady state? And the second one is, can we gain access to the bosonic distribution function? So let's answer the second question first. And we're going to consider a model of 1D fermions on a lattice. And we're going to do an interaction quench from k equals 1. This is non-interacting fermions, both to attractive and repulsive interactions, which moves us from k equals infinity down to k equals a half. We can bosonize after the quantum quench at short times, and essentially compute the Fourier transform of the density-density correlation function, the pair correlation function G2. This gives us the waiting time dependence of the static structure factor. And what we show here is that within bosonization, this has this very nice form. It has some equilibrium Luttinger liquid piece, and in particular, it's an oscillatory function with an offset that's connected to these density wave occupations, this boson occupation, exactly what we need. And as we change the parameters, we see that the time dependence is very, very different. So this is actually a very sensitive way to gain access to the individual parameters of the model. So one could do a quantum quench and then just analyze the time dependence of the static structure factor at fixed wave vector as a function of time after the quench. Measuring density correlations is much, much easier than measuring entanglement in experiments. And in fact, this technology is 15 years old. One can do it via photoassociative loss or Bragg spectroscopy, or even looking at density fluctuations with a cold atom microscope. So what we'd like to do is we'd like to perform a numerical experiment that tests this idea, where we can extract the steady state entanglement entropy from density correlations to map the thermal entanglement that we know we can get for the non-interacting bosons in the Luttinger model to this prefactor, or this thermal steady state entanglement entropy that should be the thermal entropy. All right, so let's see if it works. So we're going to focus on a particular model, the so-called JV model. This is just spinless fermions hopping on a 1D lattice, and we turn on interactions at time 0. We know the phase diagram very well from beta ansatz, mapping this thing onto the XXZ spin model. So we have a quantum liquid at kind of intermediate interactions, and then a continuous transition to a density wave, or a first order transition to a clustered solid. I mean, we're going to stay in this kind of region right here, where we can map things and actually extract the Luttinger parameter as well as the velocity exactly from beta ansatz. And our method is going to be exact diagonalization, where we can get up to very large system sizes, 26 sites, by exploiting all symmetries of the model. All right, so what we do is we do this exact diagonalization. We extract the time dependence of the static structure factor after the quench, and then are able to actually look at, so this is data right here, different curves correspond to different system sizes and different panels to different interaction strengths. We see this nice oscillatory structure predicted by the bosonization, and we can analyze without any nonlinear fitting, in fact, just using this oscillatory structure to extract all these parameters. And in particular, doing finite size scaling in the limit Q goes to 0 and L goes to infinity for different interactions, that's each of these colors right here, we can extract the boson occupation, which we'll use to compute entropies, and we can compare it to the beta ansatz and see that it basically has perfect agreement. So this approach works extremely well to get these boson occupations from a numerical experiment or a real experiment. Then at least in the for the case of exact diagonalization, we can actually compute the steady state entanglement entropy by just doing exact diagonalization and constructing in a brute force manner the reduced density matrix. This is following a lot of previous work and some recent work by us where we show how to do the finite size scaling of this quantity to extract the prefactor of the volume law. And this is just a time trace, waiting time after the quench. This is just the entanglement density in the subregion, and we know how to extract this thing to the thermodynamic limit. All right, so putting everything together, we extract at short times after the quench, we extract the boson occupation numbers from density correlations via the structure factor, and then we use this free boson formula to compute the density, the entanglement density. At long times after the quench, we use our exact diagonalization to compute the asymptotic entanglement entropy density. Putting everything together, we find that the agreement that we hypothesized works extremely well. This is the entanglement density as a function of interaction strength. The red here is coming from the short time dependence of density-density correlations, in other words, from the bosons, or the structure factor. And the triangles here come from the actual ED of the underlying fermions. Works extremely well over a large range of interactions, and in fact, if we look at the ratio, it's equal to 1 as a function of v over j within error bars coming from the uncertainty in this time asymptotic extrapolation process. So I encourage you, if you'd like more details, to have a look at this paper and look at our code right here. Thank you.